When people think of Jupiter's moons, they think of Europa. The cracked ice, the hidden ocean, the chance of life. Europa dominates every headline, every documentary, every list of places we should explore next. But orbiting the same planet, close enough to see from Europa's surface, is a moon so large it dwarfs Mercury. A moon with an ocean that may hold more water than every drop on Earth. A moon that generates its own magnetic field, something no other moon in the entire solar system does. A moon whose metallic core, according to a study published just weeks ago, may still be forming right now. Ganymede has been standing in plain sight this entire time. And what it hides may be darker than anything Europa ever promised. If you enjoy science that makes you rethink what you thought you already knew, consider hitting like and subscribing. It helps more than you realize, and we never take it for granted. Are you comfortable? Now, let's begin. If you asked 100 people to name the most important moon of Jupiter, almost every single one of them would say the same word: Europa. It has become the automatic answer, the reflexive choice, the moon that shows up in every documentary about alien life, every shortlist of places humanity should visit next, every conversation about where biology might exist beyond Earth. And to be fair, there are reasons for that. Strong reasons. Europa is one of the most compelling worlds in the solar system. Its surface is a cracked, fractured shell of water ice, geologically young by planetary standards, resurfaced so recently that large impact craters are surprisingly rare. Beneath that ice lies an ocean of liquid salt water, kept warm not by sunlight, but by the relentless gravitational kneading of Jupiter itself. The tidal forces that Jupiter exerts on Europa flex and squeeze the moon's interior, generating heat deep below the frozen crust. That heat keeps the water liquid, and that liquid water sits in direct contact with a rocky seafloor, a combination that on Earth produces hydrothermal vents, the very environments where some scientists believe life on our own planet may have first begun. Europa's ice shell is thought to be relatively thin, perhaps 10 to 30 kilometers in most models. That thinness matters enormously, because it means the ocean underneath is not locked away behind hundreds of kilometers of frozen barrier. It is close to the surface. Close enough that material from the ocean might occasionally reach the top. Close enough that plumes of water vapor may have been spotted erupting through cracks in the ice, venting material from the interior directly into space. The Hubble Space Telescope captured what appeared to be evidence of these plumes in 2012 and again in 2014 and 2016. The observations were tantalizing but not definitive. The data was at the very edge of what Hubble could resolve. Some researchers remained cautious, others were electrified. If Europa is actively venting ocean water into space, then a spacecraft would not even need to land. It could fly through the plume and sample the ocean directly. That single idea reshaped planetary exploration priorities for a generation. NASA committed billions of dollars to the Europa Clipper mission, which launched in October of 2024 and is now on its way to the Jupiter system with an expected arrival in 2030. Its job is not to land on Europa. Not yet. Its job is to perform dozens of close flybys, mapping the surface, measuring the ice thickness, analyzing the composition of whatever material the moon is releasing, and determining once and for all whether Europa's ocean has the chemistry necessary for life. Europa Clipper is one of the most ambitious planetary science missions ever built. Its instrument suite is extraordinary. Its science goals are precise, and its target, Europa, has been carefully selected as the single most promising place in the outer solar system to search for biological activity. That is the weight Europa carries. That is the assumption the entire field has organized itself around. Europa is the one. Europa is where the answer is, and nobody questions it. Almost nobody even pauses to ask whether the assumption is complete, whether the emotional and scientific focus on Europa might be leaving something out, something large, something close, something that has been sitting in the same system, orbiting the same planet, visible in the same telescope frame for as long as anyone has been looking. To understand why, you need to understand the system Europa belongs to. Because Europa is not alone around Jupiter. It is one member of a family, and the dynamics of that family are part of what makes the oversight so striking. Jupiter has 95 known moons as of the most recent count. Most of them are small, irregularly shaped, captured objects that orbit far from the planet in chaotic, tilted paths. They are debris, leftovers, gravitationally adopted wanderers that Jupiter swept up over billions of years. They are scientifically interesting in their own way, but they are not what defines the Jovian system. What defines the Jovian system is the 4 largest moons, the Galilean moons, named after Galileo Galilei, who observed them through his telescope in 1610, making them the first objects ever discovered orbiting another planet. Their discovery was one of the critical pieces of evidence that the Earth was not the center of the universe. 4 points of light moving around Jupiter in an orderly procession, proving that not everything revolves around us. The 4 Galilean moons, in order of distance from Jupiter, are Io, Europa, Ganymede, and Callisto. Each one is a world unto itself. Each one is radically different from the others, and together they form a miniature planetary system that mirrors the diversity of worlds you would find orbiting a star. But they are not independent actors drifting through their orbits at random. The 3 innermost moons, Io, Europa, and Ganymede, are locked together in one of the most elegant gravitational relationships in the solar system. It is called the Laplace resonance, named after the French mathematician Pierre-Simon Laplace, who first described its dynamics. The resonance works like this. For every single orbit Ganymede completes around Jupiter, Europa completes exactly 2, and Io completes exactly 4. Their orbital periods are locked into a precise 1:2:4 ratio, maintained by the gravitational pull they exert on each other every time they pass close together at fixed points in their orbits. This is not a coincidence. It is a gravitational engine. Each time Io swings past Europa, and each time Europa swings past Ganymede, the moons tug on each other in exactly the same orbital position. Those repeated tugs prevent the orbits from circularizing completely. They force each moon's orbit to remain slightly elliptical, slightly eccentric, which means the distance between each moon and Jupiter changes continuously over the course of every orbit. And because Jupiter's gravitational pull depends on distance, that changing distance means the tidal force on each moon fluctuates constantly. The moon is stretched and compressed in a rhythmic cycle that pumps energy into its interior as heat. This is tidal heating. It is the mechanism that turns Io into a volcanic inferno, that keeps Europa's ocean liquid, and that contributes more quietly and less dramatically to the warmth inside Ganymede. The Laplace resonance connects all 3 moons into a single thermodynamic system where the gravitational dance between them determines how much internal heat each one receives. Io, closest to Jupiter and most strongly affected, gets the most. Europa, second in line, gets enough to maintain a liquid ocean beneath thin ice. Ganymede, the outermost of the three resonant moons, gets the least. But it still gets some, and over billions of years, even a modest amount of tidal heat, combined with radioactive decay in the rocky interior, is enough to slowly warm a world that started cold. That detail will matter enormously when we reach the deep interior of Ganymede. But for now, the point is structural. Io, Europa, and Ganymede are not isolated worlds that happen to share a planet. They are gravitationally coupled, thermally connected, and dynamically linked in a way that means you cannot fully understand any one of them without understanding the others. And yet, the public narrative treats them as if Europa exists in a vacuum, as if the other moons are scenery rather than participants in the same physical system. Io, the innermost, is the most volcanically active body in the solar system. Its surface is a violent, sulphurous hellscape of erupting lava fountains and collapsing calderas, driven by the same tidal forces that heat Europa, but amplified to a far more extreme degree by its proximity to Jupiter and its role in the resonance. Io has no ice, no ocean, no calm. It is fury made solid, a world being torn apart from the inside by Jupiter's gravitational grip. Europa, the second, is the ice world, the ocean world, the one with the thin, frozen shell and the warm, salty sea underneath, the one the missions are heading toward, the one the headlines are about. Callisto, the outermost of the four, stands apart from the resonance. It is not locked into the gravitational dance with the other three. Its orbit is more circular, its tidal heating negligible, and its surface reflects that isolation. Ancient, heavily cratered, barely changed in billions of years. It may have a subsurface ocean of its own, but the evidence is weaker than for Europa, and the scientific community treats it as the least geologically active of the group. Callisto is the elder, the unchanged, the one that recorded the early bombardment of the solar system and then simply stopped. And then there is the third one, between Europa and Callisto, locked into the resonance with Io and Europa, but receiving the gentlest tidal push. The one that most people skip over when they are listing Jupiter's moons, the one they mention in passing, the one they acknowledge exists, but rarely stop to think about. The one whose name they know, but whose nature they have never seriously examined. Ganymede. Say the name, and most people nod. They have heard it. They know it is one of the Galilean moons. They might know it is big. They might recall something about ice or an ocean, but the emotional weight they assign to it is almost nothing. It sits in the public imagination as a footnote, a supporting character. Europa's quieter, less interesting neighbour. That impression is not just incomplete, it is almost exactly wrong. And the roots of that wrong impression go back further than most people realise. They go back to the first time humanity ever saw these moons up close. In March and July of 1979, NASA's Voyager 1 and Voyager 2 spacecraft flew through the Jupiter system, returning the first detailed images of the Galilean moons. What those cameras revealed changed planetary science overnight, but the changes were not distributed evenly. Each moon produced its own headline, and some headlines were louder than others. Io stole the show entirely. Voyager 1 caught an active volcanic eruption in progress, a towering plume of sulfur dioxide rising hundreds of kilometers above the surface. It was the first time volcanism had ever been confirmed on another world. The images were stunning, alien, and immediate. Io became an instant icon of planetary violence. Europa offered something subtler but deeply provocative. The Voyager cameras revealed a surface unlike anything in the solar system, a shell of ice crisscrossed by long dark lines with almost no large craters, suggesting the surface was geologically young. Scientists immediately began speculating about what could be keeping the surface so fresh. The ocean hypothesis was not far behind. Ganymede's images told a more complicated story. The Voyager cameras showed two types of terrain: dark cratered regions and lighter grooved terrain where the ice had been fractured and resurfaced by some tectonic process. It was clearly a geologically interesting world. The grooved terrain suggested internal activity, possibly driven by the same tidal forces heating its neighbors. But the story was harder to read. The grooves didn't have the visual drama of Io's volcanoes or the eerie smoothness of Europa's ice. They required interpretation. They required patience. And in a media landscape that was processing the first close-up views of an entirely new planetary system, patience was in short supply. Ganymede was acknowledged as fascinating. It was noted as the largest moon in the solar system. Papers were written. Conferences were held. But in the public imagination, the hierarchy was already forming. Io was the dramatic one. Europa was the mysterious one. Callisto was the ancient one. And Ganymede was the big one that had some grooves on its surface. That hierarchy, set in place by the Voyager encounters of 1979, has never been seriously challenged in public discourse. It calcified over the decades that followed. When the Galileo spacecraft arrived in the mid-1990s and discovered Ganymede's magnetic field, the finding was reported in the scientific literature with appropriate astonishment. But it never penetrated the public consciousness the way Europa's ocean did. The magnetic field was invisible, the ocean was imaginable, and imagination wins every time. The pattern repeated itself as recently as 2021. In June of that year, NASA's Juno spacecraft, which had been orbiting Jupiter since 2016 to study the giant planet itself, made a close flyby of Ganymede. Juno passed within 1,038 kilometers of the surface, the closest any spacecraft had come to Ganymede in more than 2 decades. The images it returned were remarkable. High-resolution views of both the dark cratered terrain and the light-grooved regions revealed fine-scale detail that no previous camera had captured. Craters with sharp rims and complex ejecta patterns. Grooves resolving into individual ridges and troughs with shadows that hinted at their true depth. Surface textures that told stories about ice tectonics operating under conditions found nowhere else in the solar system. The images circulated widely for a few days. Science outlets ran short features. Social media shared the most striking frames. For a brief window, Ganymede was visible to the public in a way it had not been since Voyager. People saw it. They noted it. Some of them paused on the images long enough to register that this was a genuinely strange and beautiful world. Then, the news cycle moved on. Within weeks, the conversation had returned to Europa, to Mars, to the James Webb Space Telescope, to whatever was next on the list of things competing for attention. The Juno images were archived. The papers analyzing them were published in journals that most people will never read. Ganymede had surfaced briefly and then sunk back below the waterline of public awareness, exactly the way it always does. That moment, That brief appearance, followed by immediate disappearance, is the pattern in miniature. Ganymede becomes visible, people acknowledge it, and then they look away. Not because they were told to, not because someone decided it was unimportant, but because the next loud signal arrived, and the quiet one could not compete. The fact that so many people carry this hierarchy without ever questioning it is the beginning of a story that, once you follow it to the end, changes how you think about the entire Jovian system. Here is the first thing most people do not know about Ganymede. It is big. Not big the way most moons are big. Not big relative to some other minor body in the outer solar system. Big in an absolute sense. Big enough to challenge the categories we use to organize the solar system. Ganymede's diameter is 5,268 kilometers. That is wider than the planet Mercury. Not slightly wider, meaningfully wider. Mercury, the innermost planet of the solar system, the world closest to the star we orbit, measures 4,879 kilometers across. Ganymede exceeds it by nearly 400 kilometers. If Ganymede orbited the star directly instead of orbiting Jupiter, there is no question it would be classified as a planet. It has the size, it has the internal complexity, it has the geological history. The only reason it carries the word moon is because it happens to orbit a larger body. Think about what that means for a moment. There is a world in the Jovian system, right next to the moon everyone talks about, that is physically larger than one of the 8 recognized planets. And the default public reaction to it is mild acknowledgement. No urgency, no fascination, no sense that something about it deserves the kind of attention Europa receives. The question is why? Why does Europa dominate the conversation while Ganymede sits quietly in the background? Why does the smaller, thinner, less structurally complex world absorb all the emotional gravity while the larger one is treated as ordinary? The answer has almost nothing to do with science. It has to do with narrative. Europa became famous because it offered a story people could feel. A frozen world with a hidden ocean, a thin shell of ice that might crack open, plumes of water reaching into space, the possibility of life, not as a distant abstraction, but as something that might be swimming beneath a surface we could almost touch. Europa is dramatic, it is cinematic, its story has tension, mystery, and a payoff that appeals to the deepest human question of whether we are alone. Ganymede does not offer that kind of story at first glance. Its ice is thicker, its ocean is buried deeper, its surface, while geologically fascinating, does not crack and vent the way Europa's does. There are no confirmed plumes, no thin shell drama, no easy image of a spacecraft flying through a geyser and tasting the ocean below. Ganymede's story requires patience. It requires looking past the surface. It requires understanding internal structure, magnetic fields, layered ice phases, and the physics of planetary differentiation. It does not announce itself. It does not perform. And in a world where attention flows toward the loudest signal, Ganymede's quietness has been mistaken for unimportance. That mistake is not harmless. Because what Ganymede actually is, once you look closely enough to see it clearly, is not a lesser version of Europa. It is something else entirely. Something larger, stranger, and in many ways more difficult to explain. Europa's ocean sits beneath a thin ice shell and rests on a rocky floor. It is a relatively straightforward system. Ice on top, water in the middle, rock on the bottom. The water is in contact with the rock, which is good for chemistry, good for the kind of mineral interactions that could support life. The simplicity is part of what makes it appealing. You can draw a diagram of Europa's interior on a napkin, and it makes intuitive sense. Ganymede's interior does not fit on a napkin. It is layered in ways that most people have never encountered when thinking about a moon. The outermost layer is ice. Beneath the ice is an ocean of liquid salt water, vast and dark and buried under approximately 150 kilometers of frozen crust. Below the ocean, there is more ice. Not the same kind of ice that sits on top, but exotic high-pressure phases of ice. Forms that do not exist naturally anywhere on Earth's surface, compressed into crystalline structures so dense they sink below liquid water. Beneath those high-pressure ice layers sits a silicate mantle, rock, hundreds of kilometers thick. And at the very center, a metallic core made primarily of iron. Ganymede is not a simple world with a hidden puddle beneath its surface. It is a fully differentiated planetary body with a metallic core, a rocky mantle, and a hydrosphere so deep and so complex that scientists have described its internal structure using the analogy of a layered sandwich, with alternating bands of ice and liquid water stacked on top of each other, all the way down to the rock. The total thickness of Ganymede's water layer, counting all the ice and liquid combined, extends roughly 800 kilometers below the surface. 800 kilometers of water in various phases, from familiar surface ice to high-pressure exotic forms that exist only under conditions of crushing depth. For comparison, the deepest point in Earth's ocean, the Mariana Trench, reaches roughly 11 kilometers below sea level. Ganymede's hydrosphere is not deeper by a small margin. It is deeper by almost 2 orders of magnitude. And the liquid ocean itself, the actual body of salt water trapped between the upper ice shell and the high-pressure ice below, is estimated to be on the order of 100 kilometers thick. According to NASA, that single liquid layer contains more water than all the surface water on Earth combined. More water than every ocean, every river, every lake, every glacier, every raindrop on the planet you are standing on right now. Sitting inside a moon that most people think of as a footnote to Europa, this is the point where the Europa assumption begins to fracture. Not because Europa is unimportant. Europa remains one of the most extraordinary worlds in the solar system. Its thin ice, its active surface, its possible plumes, its ocean in contact with rock, all of those features are real, and all of them deserve the missions being sent to study them. But the assumption that Europa is the most significant or the most structurally extraordinary moon in the Jovian system does not survive contact with Ganymede's actual measurements. Europa's ocean is estimated to be roughly 60 to 150 kilometers deep, depending on the model. Ganymede's ocean may be comparable in thickness, but exists within a water layer nearly 10 times deeper overall. Europa's diameter is 3,122 kilometers. Ganymede's is 5,268. Europa's mass is approximately 4.8 times 10 to the 22nd kilograms. Ganymede's mass is more than 3 times larger. In every measurable dimension, in size, in mass, in the total volume of water contained within it, Ganymede exceeds Europa. And it does so while carrying something Europa does not possess and cannot replicate. Something that makes Ganymede unique, not just among Jupiter's moons, not just among the moons of the solar system, but among every moon ever discovered orbiting any planet anywhere. Ganymede generates its own magnetic field. That statement sounds simple. It is not. There are over 300 known moons in the solar system. Moons of rock, moons of ice, moons of every size and composition, orbiting gas giants and terrestrial planets and dwarf planets alike. Among all of them, across the entire known inventory of natural satellites, Ganymede is the only one that produces an intrinsic magnetic field generated by an internal dynamo. Even Mars, which is a full planet with roughly 30% more diameter than Ganymede, has lost its magnetic field. Mars had one once, billions of years ago, when its core was still molten and active. But the core cooled, the dynamo died, the field collapsed, and without it, the solar wind stripped away most of Mars's atmosphere, turning a world that may once have had rivers and lakes into the cold, dry desert we see today. Ganymede still has its field, right now, actively generated by processes happening deep inside its metallic core at this very moment. A moon with the magnetic signature of a planet sitting in the shadow of Jupiter, largely ignored by the same public that knows Europa's name by heart. That field was discovered in 1996 by NASA's Galileo spacecraft during its flybys of the Jovian system. The magnetometer on board detected a dipolar magnetic field emanating from Ganymede's interior, distinct from Jupiter's own enormous magnetosphere. The finding was startling. No moon had ever shown anything like it. The data was checked, rechecked, confirmed across multiple flybys. Ganymede was generating its own magnetic shield. The implications of that discovery rippled through planetary science for years. A magnetic field requires a dynamo. A dynamo requires a liquid metallic core in motion. A liquid metallic core in motion requires heat, energy, and a mechanism to sustain convection over geological time. For a moon to maintain all of that billions of years after its formation is not trivial. It is extraordinary. It raises questions about what is happening inside Ganymede that is not happening inside any other moon in the solar system. And the answer to that question, which researchers have been pursuing for 3 decades, and which received a dramatic new chapter just weeks ago, takes us into the deep interior of a world that is not behaving the way anyone expected. Ganymede is not a quiet moon. It is not Europa's simpler, less interesting sibling. It is a world with the internal architecture of a planet, the water volume of a hidden ocean system that dwarfs anything on Earth, and a magnetic identity that stands alone among every natural satellite ever observed. The assumption that Europa is the moon that matters most around Jupiter is not wrong because Europa is unimpressive. It is wrong because it leaves out the single largest moon in the solar system. A moon whose size, structure, and magnetic field suggest that whatever is happening inside it is more complex, more layered, and more actively sustained than the quiet surface lets on. And what is happening inside it is far stranger than most people realize. Because in May of 2026, a study published in one of the most respected journals in the world proposed that Ganymede's metallic core is not a relic from the distant past. It is still forming, right now. Billions of years after the moon came into existence, iron is still sinking toward the center, still assembling the core, still powering the dynamo that produces the only moon-generated magnetic field in the known solar system. That discovery changes the picture entirely. It means Ganymede is not a frozen archive of ancient processes. It is an active world, still differentiating, still evolving internally, still producing effects that no other moon can match. And the deeper you look into what those effects mean, the more the comparison with Europa stops feeling like a rivalry and starts feeling like a warning. Because Ganymede is not hiding less than Europa. It may be hiding more. And the architecture of what it hides is where this story goes next. From the outside, Ganymede looks like a muted grey sphere. Its surface is a patchwork of two distinct terrain types: dark ancient regions pockmarked with impact craters, and lighter grooved terrain where tectonic activity long ago fractured and resurfaced the ice into parallel ridges and valleys. Compared to the vivid sulfur oranges of Io or the jagged crisscrossing lineae of Europa, Ganymede's face is understated. It does not scream for attention. It does not advertise what it carries inside. That restraint is misleading, because the interior of Ganymede is one of the most structurally elaborate places in the solar system. And understanding why begins with a single physical fact that separates Ganymede from nearly every other icy body we have studied. It has enough mass, enough gravity, and enough internal depth that the water inside it does not behave the way water behaves on Earth, or inside smaller moons like Europa or Enceladus. At Ganymede's scale, water is forced into states of matter that most people have never heard of. States that do not exist naturally anywhere on the surface of our planet. States that turn a familiar substance into something alien. On Earth, water freezes into a single form of ice. The ice in your glass, the frost on your window, the glaciers covering Greenland and Antarctica, all of it is the same crystalline structure. Scientists call it Ice 1. Its molecules arrange themselves in a hexagonal lattice, open and relatively spacious at the molecular level. That openness is the reason ice floats. It is less dense than the liquid water beneath it, a quirk of chemistry that keeps Earth's oceans from freezing solid from the bottom up. Inside Ganymede, the pressure changes everything. As you descend through the ice shell and into the ocean beneath, the weight of the material above increases with every kilometer. The deeper you go, the harder the water molecules are squeezed together. At a certain depth, roughly 150 kilometers below the surface, the pressure becomes so intense that if any water freezes at those conditions, it no longer forms the familiar hexagonal structure. Instead, the molecules are forced into tighter arrangements, packing themselves into denser crystal lattices that are heavier than liquid water. These are the high-pressure ice phases. Ice 3, Ice 5, Ice 6. Each one represents a different molecular geometry, a different way the water molecules stack under the crushing weight of everything above them. And each one sinks rather than floats. A researcher at NASA's Jet Propulsion Laboratory once described the transition by comparing it to rearranging shoes in a suitcase. At low pressure, the molecules sit loosely, like shoes tossed in at random. At high pressure, they reorganize, finding compact configurations that take up less space and weigh more per unit volume. The ice becomes so dense it drops through liquid water like a stone through air. This is not a theoretical curiosity. It is the defining structural feature of Ganymede's interior. Because these dense ice phases exist, Ganymede's water layer is not a simple system of ice on top and liquid underneath. It is a complex, stratified column where different phases of water coexist at different depths, separated by boundaries defined by pressure and temperature, not by simple freezing. The model that best captures this structure was developed by Steve Vance and his colleagues at JPL, and has been refined over more than a decade of work. In its most detailed form, the model describes Ganymede's interior as something resembling a layered sandwich. At the top, a shell of ordinary Ice 1, the familiar kind, forms the surface crust. Below that crust, at a depth of roughly 100 to 150 kilometers, the ice gives way to liquid. A vast saltwater ocean, dark and pressurized, extends downward. But the ocean does not rest on rock. Beneath the liquid layer, the pressure forces water back into solid form, this time as dense, high-pressure ice. Ice 5 and Ice 6 dominate these deeper layers, forming a thick, frozen basement between the ocean above and the silicate mantle below. In some versions of the model, the layering is even more complex. Depending on the exact temperature profile and salt content of the water, there may be additional thin liquid layers sandwiched between different high-pressure ice phases. The interior becomes not a single ocean beneath a single shell, but a stacked sequence of frozen and liquid layers, each with its own chemistry, its own pressure regime, its own relationship to the layers above and below. Vance informally described this as a club sandwich. Multiple slices of ice, multiple layers of ocean, stacked from the surface all the way down to the rock. The total depth of this water column, counting every ice phase and every liquid layer from the surface down to where silicate rock begins, is approximately 800 kilometers. That number deserves a moment of stillness. 800 kilometers of water in various forms, occupying nearly a third of the moon's total radius, sitting above a rocky mantle that itself extends for over 1,000 kilometers before reaching the metallic core at the center. Ganymede is not an ice ball with a puddle inside. It is a differentiated world with a hydrosphere so deep that it dwarfs anything in our direct experience. A world where water undergoes phase transitions that require pressures found nowhere on Earth's surface. A world whose internal architecture rivals the structural complexity of terrestrial planets. And this is where the comparison with Europa becomes scientifically important in a way that goes beyond mere size. Europa's ocean is in direct contact with its rocky seafloor. There are no intervening layers of high-pressure ice separating the water from the rock. This contact matters profoundly for chemistry. On Earth, the most biologically productive environments in the deep ocean are places where seawater meets hot rock. Hydrothermal vents where mineral-laden fluids pour out of the seafloor and feed ecosystems that survive entirely without sunlight. The chemical exchange between rock and water, the dissolution of minerals, the release of hydrogen, sulfur compounds, and other chemical energy sources. This is what many astrobiologists consider the essential ingredient for sustaining life in the absence of photosynthesis. Europa has that contact. Its ocean touches rock. And if there is volcanic or hydrothermal activity on that rocky seafloor, driven by the tidal heating from the Laplace resonance, then Europa's ocean could be receiving a continuous supply of the chemical building blocks that life requires. This is the core of Europa's habitability argument, and it is powerful. Ganymede's ocean does not have that contact. Between the liquid water and the silicate mantle lies a thick layer of high-pressure ice. Hundreds of kilometers of Ice 5 and Ice 6 compressed to densities greater than liquid water, sitting like a frozen wall between the ocean and the rock below. Any chemical exchange between Ganymede's ocean and its rocky interior must pass through this barrier, and high-pressure ice, while not perfectly impermeable, is not a good conductor of dissolved minerals and gases. It is a filter that dramatically slows the kind of rock-water interaction that Europa enjoys directly. This has significant implications. If the key to habitability is ocean rock contact, then Europa's simpler structure gives it a clear advantage. Ganymede's ocean, despite being vastly larger, may be chemically isolated from the very minerals that biology needs. It is a bigger ocean in a tighter prison. More water, but less access to the ingredients that might make that water biologically productive. But the isolation may not be absolute. Vance's research on the club sandwich model specifically explored how dissolved salts could change the picture. Salts like magnesium sulfate, which spectroscopic observations of Ganymede's surface suggest may be present in the ocean, lower the melting point of ice under pressure. At the boundaries between different high-pressure ice phases, where temperatures hover close to the transition point between solid and liquid, even a modest concentration of dissolved salts can keep thin films of brine from freezing entirely. These films would not be oceans in any conventional sense. They would be narrow, salty, wet layers threading through the dense ice at phase boundaries, persisting because the salt depresses the freezing point just enough to prevent the water from locking into a crystal lattice. The significance of these brine films is not their volume, it is their connectivity. If they exist at multiple phase boundaries within the high-pressure ice stack, they could form a network of thin liquid conduits, linking the rocky mantle far below to the main liquid ocean above. Minerals dissolved in water at the rock interface would migrate upward through these briny pathways, slowly, over geological timescales, but persistently. The transport would not be fast. It would not resemble the vigorous hydrothermal circulation that Europa's ocean rock interface might support, but it would mean that Ganymede's ocean is not perfectly sealed. It is receiving chemical input from the rock, just through a far more labyrinthine and patient route than anything Europa requires. The 2026 cryovolcanism study, which identified candidate volcanic vents on the surface carrying salt signatures, provides circumstantial support for this picture. If salts from the deep interior can reach the surface, they must have passed through the entire ice column. That implies the column is not a hermetic barrier, but a slow, leaky one, permeable enough over billions of years to allow material transport from bottom to top. Whether this slow seepage is sufficient to sustain any kind of chemistry, let alone biology, remains an open question. It is one of the specific questions the JUICE mission's compositional analysis instruments are designed to address. But the possibility itself changes the character of Ganymede's ocean. It is not simply a vast inert body of water trapped in an ice prison with no connection to the world below. It may be a vast body of water connected to its rocky interior through a network of thin brine channels that no other ocean world in the solar system possesses. A plumbing system made of salt and pressure that operates on timescales so long they are invisible to any single spacecraft flyby. And the ocean itself, the main liquid body sitting between the upper ice shell and the high-pressure ice below, is an environment unlike anything in human experience. Try to picture it. You are floating in darkness. Above you, roughly 150 kilometers of frozen crust blocks every photon of sunlight. No light has ever reached this ocean. The water is salty, pressurized, and cold by human standards, but warm enough to remain liquid under the specific pressure conditions at this depth. The temperature hovers near the boundaries of what the phase diagrams allow. A degree colder, and the water around you would not freeze into the ice you know from Earth. It would transition into a high pressure phase and sink beneath you, falling away into the dense ice layer below. And that is the most disorienting feature of this ocean. Its floor is not rock. Its floor is ice. But not the kind of ice that floats in your glass. The kind that is denser than the water you are swimming in. The kind that forms only under pressures that would crush any structure ever built by human beings. You are in an ocean bounded entirely by water in various states. Above you, familiar ice. Below you, exotic ice. Around you, liquid. There is no rock interface, no mineral-rich seafloor, no volcanic vent glowing in the dark. The entire environment is water interacting with itself across phase boundaries defined by pressure. On Earth, every ocean ultimately rests on something else. Rock. Sediment. A geological boundary between liquid and solid that separates water from the planet beneath it. Ganymede's ocean rests on a denser version of itself. It is an ocean whose floor is made of the same substance as the ocean, just in a different state. That is a kind of planetary environment that exists nowhere else in our direct experience, and for which we have no intuitive framework. The point is not that Ganymede is a better or worse candidate for life than Europa. The point is that the two worlds are fundamentally different kinds of ocean worlds. Europa is an ocean in contact with rock. Ganymede is an ocean sealed within its own substance, bounded above and below by different phases of the same material it is made of, potentially connected to the distant rock below only through thin, briny threads that weave through hundreds of kilometers of dense ice. Both are extraordinary, but the nature of their potential and the nature of their mystery is different. And Ganymede's version of the mystery, a vast ocean cut off from its own rocky interior by exotic ice that does not exist on Earth, is in many ways the stranger and more unsettling of the two. Below the water, below all the ice phases, below the ocean, Ganymede's silicate mantle begins. This rocky shell, composed primarily of silicate minerals, extends inward for approximately 1,020 kilometers in current models. It is a substantial layer, comparable in thickness to Earth's own mantle relative to total body size. The rock is warm, it is under pressure, and it is the source of the heat that helps maintain at least some of the liquid water above it. Through a combination of residual formation energy, radioactive decay, and tidal heating from Jupiter's gravitational influence. The tidal heating contribution at Ganymede is modest compared to what Io and Europa experience. Ganymede sits furthest from Jupiter among the three moons locked in the Laplace resonance, and tidal force drops sharply with distance. But modest does not mean zero. Over 4.5 billion years, even a small but persistent tidal heat source, working in concert with the heat generated by radioactive elements like uranium, thorium, and potassium within the silicate mantle, accumulates. It warms the interior gradually, degree by degree, across geological time. And that slow, patient warming is central to what researchers now believe is happening at the very center of the moon. Below the mantle sits the core, and this is where Ganymede's story diverges from what anyone expected. For decades, the standard picture of Ganymede's core was straightforward. Planetary scientists assumed that early in the moon's history, within the first few 100 million years after formation, Ganymede's interior heated up enough to differentiate. Dense metallic iron sank to the center. Lighter silicate rock floated above it. The process completed relatively quickly, the core formed, and then it began the slow, inevitable process of cooling. As the core cooled, convection in the liquid iron generated a magnetic dynamo, producing the magnetic field that the Galileo spacecraft detected in 1996. This was a clean story. It was consistent with how we understand core formation on Earth and other differentiated bodies, and it was wrong. Or at the very least, it was built on an assumption that could not hold. The problem was the starting temperature. Earth formed hot. The accretion process, the giant impacts, the gravitational energy released as material piled together, all of it heated the young Earth to the point where iron could melt and sink almost immediately. Differentiation happened fast because the planet was born with enough thermal energy to drive it. Ganymede did not form the same way. It formed in the circumplanetary disk around Jupiter, a cooler, quieter environment than the violent inner solar system where Earth assembled. Multiple formation models have shown that Ganymede likely accreted too cold to differentiate immediately. It did not start with a pre-formed metallic core. It started as a relatively homogeneous mix of rock, metal, and ice, cold enough that the iron was locked in place within the silicate matrix, rather than sinking freely to the center. This created a contradiction that planetary scientists recognized, but struggled to resolve. If Ganymede formed cold, how did it end up with a metallic core? And if the core took a long time to form, how is the dynamo still running billions of years later? A dynamo driven by a cooling core should have a limited lifespan. At some point, the core either freezes solid or reaches thermal equilibrium, convection stops, and the magnetic field dies. That is exactly what happened to Mars. Mars had a dynamo once, powered by its cooling core, but the core cooled past the point where convection could be sustained, and the field shut down. Mars is a significantly larger body than Ganymede, yet its dynamo is long dead. Ganymede's dynamo is alive. In May of 2026, a team led by Kevin Trin, at the time completing research through Caltech and the Jet Propulsion Laboratory, published a study in the journal Science Advances that proposed a resolution to this contradiction. The paper is titled Powering Ganymede's Dynamo with Protracted Core Formation. Its conclusion is striking. Ganymede's metallic core may not have formed in the distant past. It may still be forming right now. The mechanism works like this. Ganymede began cold, without a pre-existing core. Over billions of years, its interior slowly warmed through the cumulative effects of radioactive decay in the silicate minerals and tidal heating from Jupiter. As temperatures in the deep interior gradually rose, pockets of iron within the rocky mantle began to melt. Once molten, the dense iron liquid migrated downward under gravity, sinking through the silicate matrix and accumulating on a growing protocore at the center. This process did not happen all at once. It did not require a catastrophic heating event. It happened slowly, incrementally, across the full span of Ganymede's 4.5 billion year history. Iron melt forming in the mantle, descending under its own weight, arriving at the protocore, releasing gravitational energy as it settled. That energy, the heat released by the ongoing accumulation of dense metal onto the growing core, is itself a source of convection. The falling iron stirs the liquid metal already present, creating the churning motion necessary to sustain a dynamo. In this model, Ganymede's magnetic field is not the fading echo of an ancient core slowly losing its heat. It is the active signature of a core that is still being built. Each new parcel of iron that sinks from the mantle and arrives at the protocore contributes energy that drives convection, which generates the magnetic field that we detect from space. Trine and his colleagues modeled this process using the iron and iron sulfide phase diagram, the map of how iron and sulfur mixtures behave at different temperatures and pressures. The choice of iron sulfide is critical. Iron sulfide has a significantly lower melting point than pure iron. In a cold start scenario, where the deep interior is warming gradually over billions of years, iron sulfide would be among the first metallic components to cross the melting threshold. This sulfur-rich melt, dense and fluid, would migrate downward first, beginning the process of core assembly long before the temperatures reach the point where pure iron could melt. The sulfur-rich melt would settle at the center, forming the earliest seed of the protocore. As the interior continued to warm, progressively more iron-rich compositions would cross their melting points. These heavier, less sulfur-rich melts would follow the same path downward, accumulating on top of the existing sulfur-rich core material. The result is a core that is not compositionally uniform, but stratified, with sulfur-rich material at the center and progressively iron-rich layers building outward over time. This compositional stratification matters for the dynamo because it affects how convection operates within the liquid metal. A compositionally stratified core can sustain convection through a mechanism called compositional buoyancy, where lighter sulfur-rich fluid rises and denser iron-rich fluid sinks, creating circulation patterns that are distinct from the purely thermal convection that drives Earth's dynamo. The interplay between thermal and compositional convection in a growing core creates a dynamo that is fundamentally different from any that has been modeled for a planetary body before. The study's computer models showed that under plausible conditions, this process could sustain a dynamo for billions of years, not by cooling an already formed core, but by growing one. The energy source is gravitational differentiation itself, the ongoing separation of heavy metal from lighter rock, a process that has no equivalent on any other known moon. The co-authors of the paper, including Stephen Vance of JPL and Douglas Hemingway of the University of Texas at Austin, emphasize that the model does not rule out other explanations for Ganymede's dynamo. A cooling-driven mechanism remains possible if Ganymede's formation was hotter than current models suggest. But the protracted core formation hypothesis has a specific advantage. It aligns with the formation studies that consistently show Ganymede starting cold. It does not require assumptions about the initial state that contradict the best available formation models. As Treen stated directly, many formation studies suggest that Ganymede formed too cold to start with a metal core, and many dynamo studies assume that Ganymede formed its metal core when the moon itself formed, the way Earth did. Both of those things cannot be simultaneously true. The protracted core formation model resolves the conflict by removing the assumption that differentiation had to happen early. It lets Ganymede form cold and still end up with an active dynamo today. The researchers also noted that the JUICE mission, currently en route to Jupiter, will be able to test predictions of the protracted core formation model. The compositional stratification of the core would produce a magnetic field with specific characteristics, particular ratios between the dipole and higher-order multipole components that differ from what a fully formed, cooling core would generate. Precise mapping of Ganymede's magnetic field during the orbital phase of the mission could distinguish between the two scenarios, providing the first direct observational test of whether a moon's core is still assembling itself 4.5 billion years after formation. This discovery reshapes the entire understanding of what Ganymede is. It means the moon is not a static body preserving a frozen snapshot of ancient processes. It is an actively evolving world whose deep interior is still undergoing fundamental structural change. Material is still moving inside it, metal is still sinking, energy is still being released, the core is still assembling. Among the more than 300 moons catalogued in the solar system, not a single other one is known or even suspected to be undergoing this process right now. Earth completed its core formation within the first tens of millions of years of its existence. Mars finished long ago. Mercury, the Moon, Io, all differentiated early and have been cooling since. Ganymede, according to this model, is still in the middle of it. 4.5 billion years in, and it has not finished becoming what it is. The implications extend beyond the dynamo. If the core is still growing, then the thermal structure of the entire interior is evolving. The mantle above the core is losing iron, which changes its density and its convective behavior. The heat released by ongoing differentiation propagates upward, influencing the temperature at the base of the hydrosphere, which in turn affects which ice phases are stable, where liquid water can persist, and how thick the ocean layers are. In other words, Ganymede's interior is not a fixed structure that was set in place billions of years ago. It is a living system, still adjusting, still reorganizing, still releasing energy from a process that most planetary bodies completed in their infancy. That realization casts the entire layered sandwich structure in a different light. The ocean, the ice phases, the rocky mantle, none of these layers are permanent in the way we typically think of geological structures. They are the current configuration of a system that is still being driven by deep internal change. The sandwich is still being assembled. The layers are still shifting. And the energy powering that assembly has a measurable, detectable consequence at the surface. Not at the surface of the ice, not in the crust or the terrain or the craters, at the surface of the magnetic field. Because the same process that is building Ganymede's core, the sinking of dense iron melt through the mantle, the accumulation of liquid metal at the center, the gravitational stirring that sustains convection, is the process that generates the most anomalous feature Ganymede possesses. The feature that no other moon in the known solar system shares. The feature that, once you understand what it actually means, makes Ganymede impossible to dismiss as Europa's quieter companion. Ganymede's magnetic field is not a relic. It is not a remnant. It is not the last gasp of a dying dynamo running out of heat. It is the active, ongoing product of a world that is still building itself from the inside out. A world that started cold and has been slowly, patiently, over billions of years, becoming something more complex than it was at birth. No other moon does this. No other moon in the solar system generates its own magnetic field. Not Titan, which is nearly as large. Not Europa, which gets all the attention. Not Callisto, not Triton, not any of the hundreds of small captured irregulars orbiting the giant planets. Among every natural satellite ever observed, across every system studied by every spacecraft humanity has ever launched, Ganymede stands alone. And the reason it stands alone is not a surface feature. It is not a visible crack or a dramatic plume or a photogenic eruption caught on camera. It is something invisible, something buried, something that can only be detected by a magnetometer flying close enough to feel it. The story of that detection, what it revealed, what it means for Ganymede's relationship to Jupiter's own colossal magnetic environment, and what new research suggests about the ocean currents flowing in the darkness far below the ice, changes the scale of this story entirely. Because the magnetic field does not just tell us something about Ganymede's core, it tells us something about Ganymede's ocean. It tells us the ocean is not still. It is not a passive reservoir of buried water sitting quietly between layers of ice. The water is moving. It is circulating. It is flowing through Ganymede's own magnetic field and generating secondary signals that scientists are now learning to read. The ocean is not asleep, and neither is the world that contains it. What the magnetic field actually is, what it interacts with, and what it reveals about the hidden dynamics of Ganymede's interior is where this story crosses from remarkable to deeply unsettling. And it begins with a spacecraft that flew past a quiet-looking moon in 1996 and detected something that should not have been there. In December of 1995, NASA's Galileo spacecraft entered orbit around Jupiter after a 6-year journey from Earth. Its mission was to study the giant planet and its moons in more detail than any previous spacecraft had achieved. Over the next 8 years, Galileo would make multiple close flybys of each of the 4 Galilean moons, returning data that would transform our understanding of the Jovian system. The encounter that changed Ganymede's place in planetary science happened on June 27, 1996. Galileo flew within 844 kilometers of Ganymede's surface, close enough for its magnetometer to detect subtle features in the local magnetic environment. What the instrument recorded that day was not subtle at all. The magnetometer was designed to measure the magnetic field in the space around the spacecraft, separating the contributions from Jupiter's own enormous magnetosphere from any local signals that might be generated by the moons themselves. Jupiter's magnetic field is the largest and most powerful planetary magnetosphere in the solar system, extending millions of kilometers into space and engulfing all 4 Galilean moons in a constant bath of magnetized plasma. Any measurement taken near one of those moons would be dominated by Jupiter's field. The challenge was identifying whether anything additional was present on top of it. As Galileo approached Ganymede, the magnetometer data began to deviate from what Jupiter's background field alone would predict. The deviations grew stronger as the spacecraft got closer to the moon. By the time Galileo reached its closest approach, the signal was unmistakable. A distinct dipolar magnetic field was radiating outward from Ganymede's interior. It had its own orientation, its own strength, its own geometry. It was not an echo of Jupiter's field. It was not an induced response from a conducting layer reacting passively to the external environment. It was an intrinsic field, generated by processes occurring inside the moon itself. The discovery was led by Margaret Kyvelson, a space physicist at the University of California, Los Angeles, who served as the principal investigator for Galileo's magnetometer. Kyvelson and her team analyzed data from that first flyby and from subsequent passes to characterize the field in detail. Their conclusion, published in the journal Nature, was definitive. Ganymede possesses an intrinsic magnetic field, dipolar in structure, with its axis tilted relative to Ganymede's rotation axis, consistent with generation by a self-sustaining dynamo operating in the moon's metallic core. But the first flyby was only the beginning. Galileo would return to Ganymede 5 more times over the following years, each encounter providing additional magnetometer data from a different geometry, a different approach angle, a different position relative to Jupiter's background field. Each pass sharpened the picture. The second flyby in September of 1996, confirmed the dipolar structure and allowed the team to begin separating the intrinsic field from the induced field. The secondary signal generated by Ganymede's conducting ocean responding to Jupiter's time-varying magnetic environment. The third encounter in 1997 provided data from a polar pass that constrained the tilt of the magnetic dipole axis. Later flybys in 2000 refined the field strength estimates and revealed hints of complexity beyond a simple dipole. Faint, higher-order multipole components that could carry information about conditions deep in the core. Each successive encounter reduced the uncertainty. What had been an astonishing but singular detection in June of 1996 became, by the end of the Galileo mission in 2003, one of the most robustly characterized magnetic fields of any body in the outer solar system. 6 independent measurements, taken at different times and from different directions, all telling the same story. Ganymede has its own internally generated magnetic field. The dynamo is real, the core is active. The field strength at Ganymede's surface is approximately 750 nanotesla. For comparison, Earth's surface magnetic field averages roughly 25,000 to 65,000 nanotesla, depending on latitude. Ganymede's field is far weaker than Earth's, but it does not need to be strong to be extraordinary. What makes it extraordinary is that it exists at all. On Earth, the magnetic field is generated by convection in the liquid iron outer core. Electrically conducting fluid rises and sinks in complex patterns driven by heat escaping from the solid inner core below. As the conducting fluid moves through the existing magnetic field, it generates electrical currents. Those currents produce their own magnetic fields, which reinforce the original field, creating a self-sustaining loop that has been operating for at least 3.5 billion years. This process, the geodynamo, is one of the most important phenomena in planetary science because the field it produces shields the atmosphere from charged particles streaming outward from the star we orbit. Without it, Earth would likely have lost its atmosphere billions of years ago, the same way Mars lost its own after its dynamo shut down. Every planet that generates an intrinsic magnetic field does so through a version of this process. Mercury has one, weak but measurable, generated by its partially liquid iron core. Jupiter has the most powerful magnetic field of any planet, driven by metallic hydrogen convection deep in its interior. Saturn, Uranus, and Neptune all have dynamos of their own, each with distinct geometries reflecting the unique conditions inside their interiors. Among moons, Ganymede stands completely alone. Not one of the other known moons in the solar system has an internally generated magnetic field. Titan, Saturn's largest moon, is nearly as large as Ganymede and possesses a thick atmosphere, but it shows no evidence of an intrinsic dynamo. Callisto, Ganymede's neighbour in the Jovian system and similar in size, has no dynamo. Io, despite its intense volcanic activity and internal heat, does not generate its own field. Triton, Neptune's largest moon and a captured Kuiper Belt object with geological activity on its surface, shows no intrinsic field. The absence is universal. Across every known natural satellite, orbiting every planet and dwarf planet in the solar system, the count of moons with self-generated magnetic fields is exactly one: Ganymede. Understanding why requires returning to the interior, to the metallic core whose ongoing formation was described earlier. But understanding what the field does, how it behaves, and what it interacts with requires looking outward. Because Ganymede's magnetic field does not exist in isolation. It exists inside the most powerful magnetic environment in the solar system, and the collision between the two creates something found nowhere else in our cosmic neighborhood. Jupiter's magnetosphere is immense. It extends roughly 5 million kilometers on the side facing the star and stretches hundreds of millions of kilometers in the opposite direction, forming a magnetic tail so long it nearly reaches the orbit of Saturn. Everything within that magnetosphere, every particle of plasma, every ion stripped from Io's volcanic eruptions, every charged particle captured from the solar wind, is controlled by Jupiter's magnetic field. The Galilean moons orbit deep inside this magnetic prison. They are constantly immersed in Jupiter's magnetized plasma. Most moons in this environment respond passively. They interact with Jupiter's field the way a rock interacts with a river. The plasma flows around them, perhaps inducing weak currents in any conducting layers they possess. But fundamentally, the moon is a passive object being acted upon by a dominant external force. Ganymede is different. Ganymede pushes back. Its intrinsic magnetic field carves out a region of space around the moon where Ganymede's own field dominates Jupiter's. This region is called a magnetosphere, and Ganymede is the only moon in the solar system known to possess one. It is small compared to planetary magnetospheres, extending roughly 2 Ganymede radii from the surface on the side facing Jupiter, and forming a compact magnetic bubble embedded within Jupiter's vastly larger bubble. The boundary where Ganymede's field meets Jupiter's field is called the magnetopause. At this boundary, the two fields interact. Jupiter's plasma, flowing past at high speed, compresses Ganymede's field on the upstream side and stretches it on the downstream side, creating a miniature version of the same kind of magnetic architecture that Earth's magnetosphere creates when it interacts with the solar wind. Inside Ganymede's magnetopause, the environment is fundamentally different from the surrounding Jovian plasma. Charged particles are diverted. Energy fluxes change. The physics of the local space environment is governed by Ganymede's own field rather than Jupiter's. Auroral emissions have been detected at Ganymede's poles, regions where Ganymede's magnetic field lines funnel charged particles downward toward the surface. The Hubble Space Telescope observed these auroral belts in ultraviolet light, confirming that Ganymede has active auroral activity driven by its interaction with Jupiter's magnetic environment. And the magnetosphere does not just exist as an abstract magnetic structure overhead. It leaves marks on the surface itself. This is one of the least discussed but most physically tangible consequences of Ganymede's unique magnetic identity, and it has no parallel on any other moon in the solar system. Jupiter's radiation environment is ferocious. The planet's enormous magnetosphere traps and accelerates charged particles, primarily electrons and ions, to enormous energies. These particles bombard the surfaces of the Galilean moons relentlessly. On Europa, on Callisto, on Io, this bombardment is essentially uniform across the surface, modified only by local geometry and each moon's position within Jupiter's magnetosphere. The particles arrive from all directions with roughly equal intensity, weathering the ice and rock through a process called radiolysis, where high-energy particles break apart surface molecules, creating new chemical species that would not form under normal conditions. On Ganymede, the pattern is completely different. The magnetic field acts as a selective shield. Near the equator, where the field lines are closed and form protective loops running from one hemisphere to the other, The surface is partially shielded from Jupiter's radiation. Charged particles are deflected by the closed field lines before they can reach the ice below. But near the poles, the field geometry changes. Ganymede's magnetic field lines open up and connect to Jupiter's field, creating funnel-shaped pathways through which high-energy particles from Jupiter's radiation belts can stream downward and slam into the surface with full intensity. The result is a moon, whose own magnetic field divides its surface into two fundamentally different radiation environments. The equatorial regions, sheltered beneath the closed field lines, experience less radiolytic processing. The ice there retains more of its original composition, appearing brighter and more reflective in spectral observations. The polar regions, exposed through the open field lines, are bombarded more intensely. The ice there shows greater evidence of chemical alteration, darker coloring, different spectral signatures, more evidence of compounds produced by radiation, breaking apart water molecules and recombining the fragments into new substances like hydrogen peroxide and ozone. Galileo observations confirmed this pattern. Ground-based spectroscopic studies reinforced it. Ganymede's surface is being differentially weathered by its own magnetic field. The equator and the poles are aging at different rates, being chemically processed by different radiation doses, developing different surface compositions, all because the moon generates a magnetic field that redirects the charged particle environment around it. No other moon does this. On every other satellite in the solar system, surface weathering by radiation is controlled entirely by the external environment, by the parent planet's magnetosphere, by the solar wind, by cosmic rays. The moon itself has no say in how its surface is processed. On Ganymede, the moon actively shapes its own surface, weathering through the magnetic field it generates internally. It is another way in which Ganymede behaves less like a moon and more like a planet, exerting internal authority over its own external environment. Those same auroral observations played a critical role in confirming the existence of Ganymede's subsurface ocean. In 2015, a team led by Joachim Saar at the University of Cologne published a study that used the auroral belts as a diagnostic tool for probing Ganymede's interior. The method was elegant. Jupiter's magnetic field rotates with the planet, completing one full rotation approximately every 10 hours. As Jupiter's field sweeps past Ganymede, it exerts a periodic forcing on Ganymede's own magnetic field. That forcing causes Ganymede's auroral ovals to rock back and forth, oscillating north and south in a rhythm tied to Jupiter's rotation period. The amplitude of that rocking, how far the auroral belts swing with each cycle, depends on what lies beneath Ganymede's surface. If Ganymede were a solid body with no conducting interior, its magnetic field would respond fully to Jupiter's forcing. The auroral belts would rock by a predictable amount, swinging freely in response to the external push. But if a layer of electrically conducting material exists beneath the surface, something like a saltwater ocean rich in dissolved ions, that conducting layer would generate its own induced currents when Jupiter's field changes. Those induced currents would create a secondary magnetic field that partially opposes the external forcing, acting as a brake on the rocking motion. The auroral belts would still oscillate, but by a smaller amount. The ocean would dampen the swing. Saar's team used the Hubble Space Telescope to observe the auroral belts over multiple Jupiter rotation cycles, carefully measuring the rocking amplitude. What they found was a dampening of roughly 2 degrees compared to the 6 degrees predicted for a moon with no subsurface ocean. The reduction was significant, far beyond measurement uncertainty, and consistent with a large, global saltwater ocean buried beneath the ice. This was the strongest evidence to date, independent of the Galileo magnetometer data, that Ganymede harbors a global subsurface ocean. And it was obtained not by probing the ice directly, not by detecting plumes or surface chemistry, but by reading the magnetic signature of the ocean through its effect on auroral emissions visible from Earth orbit. The ocean revealed itself through magnetism. What emerged was a picture of a moon operating on multiple magnetic levels simultaneously. At the deepest level, the iron core dynamo generates the intrinsic dipolar field. Above that, the buried ocean responds to Jupiter's time-varying magnetic field by producing induced currents that create their own secondary magnetic signals. And above that, the intrinsic field interacts with Jupiter's magnetosphere to create a miniature magnetosphere with its own auroral activity, its own plasma dynamics, its own boundary physics, and its own influence on the surface below. No other moon operates on all of these levels. Europa has an induced magnetic signal from its ocean, but no intrinsic dynamo. Callisto may have a weak induced signal, but no dynamo and far less certainty about its ocean. Ganymede runs the full stack. Dynamo, ocean induction, magnetosphere, auroras, differential surface weathering, all simultaneously, all interacting with each other and with Jupiter's field in a coupled system that scientists are still working to disentangle. And the story of disentanglement took a significant step forward in 2025 and 2026 with a series of studies that asked a question no one had been able to answer before. Can the ocean currents inside Ganymede be detected through the magnetic field? The idea is not new in principle. On Earth, the movement of electrically conducting salt water through the planet's magnetic field generates measurable secondary magnetic signals. These ocean-induced magnetic fields have been studied for more than 50 years using satellite magnetometers and ground-based observatories. The signals are faint, typically on the order of a few nanotesla, but they are real and they carry information about ocean circulation patterns. Ganymede presents a vastly more favourable situation for this kind of measurement than Europa. The reason is the intrinsic dynamo. On Europa, any ocean-induced magnetic signal would be generated by the interaction of ocean currents with Jupiter's external field. That signal is expected to be extremely weak, likely on the order of 1 nanotesla or less under the most favourable conditions. Detecting it would require magnetometers with extraordinary sensitivity operating in an environment dominated by Jupiter's powerful and noisy magnetic background. On Ganymede, the ocean sits inside the moon's own magnetic field. The intrinsic dipolar field generated by the core dynamo permeates the ocean. When salt water moves through that field, the interaction generates secondary magnetic signals that are amplified by the strength of the background field. A team based at Charles University published a study in 2025 estimating that the magnetic signal generated by convective flow in Ganymede's ocean could range from approximately 0.1 to 10 nanotesla, depending on the ocean's thickness, conductivity, and flow speed. A subsequent study in early 2026 refined these estimates using numerical models of rotating convection in the ocean, confirming that the signal was within the detection range of instruments aboard the JUICE spacecraft. A separate analysis published in Geophysical Research Letters in March of 2026 took the investigation further. That study modeled the coupling between Ganymede's ocean flow patterns and its internal dynamo using a kinematic induction framework. The results showed that ocean currents organized into large-scale zonal jets, bands of flow running parallel to the equator, similar to the jet streams in planetary atmospheres, could produce a distinctive magnetic signature. The spectral properties of this signature would differ from both the core dynamo signal and the induced signal from Jupiter's field, making it potentially separable with sufficiently precise measurements. The study concluded that in most realistic scenarios, a detectable magnetic signal from Ganymede's ocean circulation exists. This finding relies heavily on the presence of Ganymede's intrinsic dynamo. The internal field provides the strong magnetic background against which ocean currents act. Without it, the ocean signal would be far weaker, likely below practical detection limits. This situation, the researchers noted, contrasts sharply with Europa, which lacks an internal dynamo and where the ocean-induced magnetic signal may be beyond the practical sensitivity of both the JUICE and Europa Clipper magnetometers. Ganymede's magnetic field is not only unique, it is a tool, a window into the ocean below. If the JUICE mission can measure the ocean-induced magnetic signal with enough precision, scientists will be able to constrain the speed and geometry of ocean currents flowing in total darkness hundreds of kilometers below the ice. They will be able to determine whether the ocean circulates in organized patterns or churns chaotically. They will have access to information about a buried ocean that no camera, no spectrometer, and no radar can provide. The ocean is not still. It is moving. And its movement is writing a magnetic signature that rises through the ice, through the crust, and into space, waiting for an instrument sensitive enough to read it. This is the world that has been sitting in Europa's shadow. A world with a dynamo, a magnetosphere, auroras, an ocean writing its own magnetic signals, a surface being differentially sculpted by its own magnetic field, and a core that may still be assembling itself at this very moment. And as if the interior were not enough, the surface may also be telling a story that most people have overlooked. In May of 2026, a study led by Anizina Solomonidou of the Hellenic Space Center and published in the Planetary Science Journal identified 4 candidate cryovolcanic regions on Ganymede's surface. The team used reprocessed data from the near-infrared mapping spectrometer aboard the Galileo spacecraft, which had observed Ganymede between 1995 and 2003. By examining unusual surface depressions and flow-like structures, they identified 4 paterae, shallow depressions that may have functioned as vents through which subsurface water and volatile materials erupted onto the surface. Cryovolcanism, the eruption of water-rich and volatile materials instead of molten rock, has been confirmed on other icy moons. Enceladus, Saturn's small but geologically hyperactive moon, famously sprays plumes of water ice and organic molecules from fractures near its south pole. Europa may have its own intermittent plume activity, though the evidence remains less definitive. On Ganymede, cryovolcanism has long been suspected, but never confirmed. The grooved terrain that covers much of the surface has been interpreted as evidence of past tectonic and possibly volcanic resurfacing, but the resolution of available imagery has been insufficient to make a definitive determination. The 4 paterae identified in the 2026 study represent the strongest candidates yet. Their spectral analysis revealed distinct groupings. Some paterae showed surfaces dominated by water ice. consistent with erupted material that froze on contact with the vacuum. Others showed enrichment in salts, compounds that could originate from the buried ocean below. The presence of salt-bearing minerals on the surface near potential volcanic vents is significant because it suggests a pathway by which material from Ganymede's deep ocean could reach the surface, carrying chemical information about the interior environment. Solomonidou emphasized that these sites are priority targets for the JUICE mission. When the spacecraft enters orbit around Ganymede in late 2034, its instruments will be able to observe these regions at far higher resolution than anything Galileo achieved. If the Paterae are confirmed as cryovolcanic vents, it would mean that Ganymede's subsurface ocean is not merely a passive reservoir. It is connected, however intermittently, to the surface. Material from the deep interior can reach the outside, and that material can be studied. The JUICE mission itself represents a profound statement about Ganymede's scientific importance. Launched by the European Space Agency in April of 2023, JUICE is the first large-class mission of the Cosmic Vision program. It successfully completed a gravity assist flyby of Venus in August of 2025 after resolving a communication anomaly, and is scheduled for an Earth flyby in September of 2026. After a second Earth flyby in January of 2029, the spacecraft will arrive at Jupiter in July of 2031. The mission plan calls for roughly 3 years of observations in the Jupiter system, including flybys of Europa and Callisto. But the primary target, the world around which the entire mission architecture was designed, is Ganymede. In December of 2034, JUICE will enter orbit around Ganymede. It will be the first spacecraft ever to orbit a moon other than Earth's own. The orbital phase will last approximately 9 months, with the final phase placing the spacecraft in a low circular orbit just 500 kilometers above the surface. The instrument suite that JUICE carries to Ganymede was selected specifically to answer the questions we have been raising. The magnetometer, known as JMAG, will map Ganymede's magnetic field with precision far beyond what Galileo could achieve from its brief flybys. It will characterize the intrinsic dynamo field, separate the ocean-induced signal, and search for the subtle multipole components that could distinguish a still-growing core from a fully formed one. The Radar for Icy Moons Exploration Instrument, REM, will send radio waves through the ice shell and listen for reflections from subsurface boundaries, potentially detecting the top of the liquid ocean directly and measuring the thickness of the upper ice layer. The Gravity and Geophysics experiment will track tiny variations in the spacecraft's orbit, caused by irregularities in Ganymede's gravitational field, allowing scientists to map the internal density structure and constrain the thickness of the ocean, the ice layers, and the silicate mantle. The Magis Imaging Spectrometer will analyze the surface composition at high resolution, identifying salts, organic molecules, and other compounds that could indicate material transport from the interior. And the Janus camera system will image the surface at resolutions as fine as a few meters per pixel, revealing geological features that Galileo's cameras could never resolve. Together, these instruments will produce the most complete portrait of any outer solar system moon ever assembled. Every major question about Ganymede, the ocean structure, the magnetic field, the core dynamics, the cryovolcanic activity, the surface composition will be addressed by hardware that is already in space, already on its way, already calibrated and tested, and waiting for the encounter. The fact that the European Space Agency chose Ganymede as the primary orbital target for its flagship outer solar system mission is not an accident. It reflects a scientific consensus that has been building for decades, but has rarely reached the public. Ganymede is not Europa's lesser companion. In terms of structural complexity, magnetic uniqueness, and the sheer number of open scientific questions it presents, Ganymede may be the single most scientifically rich moon in the solar system. Europa offers the tantalizing possibility of accessible life. A thin ice shell, a warm ocean-touching rock, possible plumes carrying ocean material into space. Those are compelling reasons to explore it, and Europa Clipper will do so with extraordinary capability. But Ganymede offers something different, something that Europa cannot match. A world with an active magnetic dynamo powered by a core that is still forming. A buried ocean so deep it requires exotic ice phases just to exist. A magnetosphere carved out of Jupiter's own magnetic environment. Auroral activity driven by the collision of two magnetic fields. A surface being sculpted by the interplay between those fields. Ocean currents that may be detectable through their magnetic fingerprints. Candidate cryovolcanic vents that may connect the deep ocean to the surface. And a structural complexity that extends from the metallic core to the ice crust in unbroken, layered continuity. Europa is dramatic. Europa is photogenic. Europa tells a story that is easy to feel. Ganymede tells a story that is harder to see, but once you see it, impossible to set aside. Because the question is no longer whether Ganymede is interesting. The question is how a world this large, this complex, this magnetically unique, and this actively evolving could have spent decades being treated as background scenery, while a smaller, simpler neighbor absorbed nearly all the public fascination and emotional weight. The answer to that question, and the reason the title of this video uses the word darker, is not about a competition between two moons. It is about what happens when the most extraordinary things hide behind quiet surfaces and patient timescales. It is about the kind of reality that does not announce itself, does not perform for cameras, does not erupt on schedule for visiting spacecraft. It simply exists, massive, layered, magnetically alive, waiting. And what it implies about how we assign importance to worlds, about what we overlook when we chase the loudest signal, about what the solar system's biggest moon has been concealing while everyone looked elsewhere, is where this story ends. There is a pattern in how people decide what matters. It shows up in science, in history, in the way we build our understanding of anything large and complicated. We look at a system with many parts, and we assign importance based on which part is easiest to see. Which part gives us the strongest emotional signal? Which part tells the most immediately compelling story? The parts that are quiet, the parts that require patience, the parts whose significance lives beneath the surface, those get filed away. Acknowledged, but not absorbed. Known, but not felt. That pattern explains nearly everything about how the public has thought about Jupiter's moons for the past 30 years. Europa is the signal. Europa is the drama. Europa is the moon with the cracked ice and the hidden ocean, and the tantalizing suggestion that something might be alive down there. It is the moon that launched missions, that filled documentaries, that became synonymous with the question of whether life exists beyond Earth. And none of that is undeserved. Europa earned its place in the scientific imagination through genuine physical properties that make it one of the most important targets for astrobiology in the solar system. But the pattern held. While Europa absorbed the attention, Ganymede sat in the same orbital system, visible in the same telescope frames, known to every planetary scientist alive, and was treated as a secondary object. A large moon with some interesting features. A world worth studying eventually. A place that would get its turn when the time came. The time came. And what it revealed is not simply that Ganymede is interesting. What it revealed is that Ganymede may carry a conceptual weight that Europa, for all its fame, does not. The title of this video uses the phrase, darker reality. That phrase has a specific meaning that needs to be made explicit, because it is not saying what most people would assume on first hearing. It is not saying that Ganymede is more likely to host life than Europa. The habitability case for Europa, with its thin ice shell, its ocean in direct contact with a rocky seafloor, its possible hydrothermal chemistry, remains scientifically strong. Ganymede's ocean, buried beneath a far thicker ice crust, and separated from the rocky mantle by layers of high-pressure ice, presents a more ambiguous picture for biology. The high-pressure ice phases at the base of the ocean may insulate the water from the mineral-rich rock below, reducing the chemical exchange that many astrobiologists consider essential for sustaining life. It is not saying that Ganymede is simply bigger and therefore more impressive. Size alone does not carry conceptual weight. A large, simple, inert object is not more unsettling than a small, active, complex one. If Ganymede were merely a bigger version of a dead, undifferentiated ice world, its size would be a curiosity and nothing more. And it is not saying that there is a competition between the two moons in which one must win and the other must lose. That framing misses the point entirely. The darker reality is not about rivalry. It is about a failure of perception. A failure that, once you see it clearly, changes how you think about the entire practice of exploring the solar system. Here is what the phrase means. Ganymede is a world that generates its own magnetic field, the only moon among more than 300 in the solar system to do so. Its metallic core may still be forming right now, 4.5 billion years after the moon came into existence. Its ocean contains more water than every body of water on the surface of our planet combined, buried beneath a hydrosphere so deep and so pressurized that water is forced into crystalline phases that do not exist naturally anywhere on Earth. Its magnetic field carves out a miniature magnetosphere within Jupiter's colossal magnetic environment, producing auroral activity at its poles and enabling the detection of ocean currents flowing in total darkness hundreds of kilometers below the surface. Its surface may bear the scars of cryovolcanic vents that once connected the deep interior to the outside, and the European Space Agency chose it as the primary orbital target for the most ambitious outer solar system mission ever launched. A decision that reflects a scientific consensus about Ganymede's importance that the public has never fully absorbed. All of that has been true for years. Some of it has been true for decades. And the default emotional response to Ganymede among people who are not planetary scientists has been indifference, mild acknowledgement, a footnote in the Europa story. That is the darker reality. Not that Ganymede contains some hidden horror or some catastrophic secret, but that one of the most structurally extraordinary worlds in the solar system has been sitting in plain sight, radiating evidence of its own complexity, and the collective attention of the public, the media, and much of the popular science communication ecosystem looked right through it. The unsettling part is not what Ganymede is hiding. The unsettling part is that it was never really hiding at all. Consider what it means for a world to generate its own magnetic field. On Earth, the magnetic field is so fundamental to the planet's habitability that without it, the world as we know it would not exist. The field deflects charged particles from the solar wind, protecting the atmosphere from being eroded into space. It shields the surface from radiation that would otherwise sterilize exposed environments. It creates the conditions under which complex life, biology that depends on a stable atmosphere and moderate radiation levels, can develop and persist. When Mars lost its magnetic field, it lost its atmosphere. When it lost its atmosphere, it lost its surface water. When it lost its surface water, it lost whatever chance it may have had for sustained biological complexity. The death of a magnetic dynamo is, in planetary terms, one of the most consequential events that can happen to a world. It is the difference between a living planet and a dead one. Ganymede's dynamo has not died. It is running right now, and according to the 2026 study, it may be running not because of residual heat from an ancient core formation event, but because the core formation itself is ongoing. Iron is still sinking through the silicate mantle. Gravitational energy is still being released. Convection in the liquid metal is still being sustained by a process that has no confirmed parallel anywhere else in the known solar system. This means Ganymede is not a world that completed its internal development and then began the long, slow decline toward quiescence. It is a world that is still becoming, still differentiating, still assembling the deep interior that produces its most distinctive feature, 4.5 billion years old, and not yet finished. The philosophical weight of that realization is easy to miss if you are focused on whether a moon has life or whether a spacecraft can fly through a plume, but it should not be missed. A world that is still forming its core is a world that operates on a timescale and according to an internal logic that is fundamentally different from any other moon we have ever studied. It suggests that the standard categories we use to organize moons, active versus inactive, differentiated versus primitive, geologically alive versus geologically dead, may be too coarse to capture what Ganymede actually represents. It occupies a category that did not exist before its properties were fully understood. A moon with the structural identity of a planet, the magnetic autonomy of an independent world, and an interior that is still undergoing the most basic process of planetary formation, and it occupies that category quietly, without plumes visible from orbit, without a cracked young surface that photographs well, without the narrative simplicity of a thin ice shell and a warm ocean pressing against rock. Ganymede's story is harder to tell than Europa's. It requires understanding magnetic dynamos, high-pressure ice physics, core formation thermodynamics, and the electromagnetic coupling between a moon and its parent planet's magnetosphere. It does not reduce easily to a single sentence or a single image. It resists the kind of compression that makes a topic go viral. That resistance is itself part of the darker reality. Because it means the worlds that are most likely to be overlooked are not the ones that are least important. They are the ones whose importance is hardest to communicate quickly. The worlds that require patience, the worlds that reward depth over spectacle, the worlds whose most extraordinary features are invisible to cameras and legible only through instruments that most people have never heard of. Ganymede's magnetic field cannot be photographed. Its ocean cannot be seen. Its core cannot be imaged. Its high-pressure ice phases do not reflect light in dramatic colors. Everything that makes Ganymede extraordinary is buried. literally buried beneath hundreds of kilometers of ice, rock, and metal, accessible only through magnetometers, gravimeters, radar sounders, and the patient mathematical work of people who spend their careers decoding signals that arrive as numbers on a screen. Europa, by contrast, offers ice ridges that look striking in processed images. Reddish-brown streaks of surface chemistry that invite speculation. Possible plume activity that creates dramatic visuals, even when the evidence is marginal. Europa is photogenic in a way that Ganymede is not. And in an era where attention is the scarcest resource, photogenicity matters more than it should. The result is a systematic bias toward the visible over the significant, toward the dramatic over the profound, toward the world that performs for the camera over the world that reveals itself only to instruments and equations. That bias is not limited to moons. It operates across the entire practice of science communication. The discoveries that reach the public are disproportionately the ones that can be captured in a single image or summarized in a single headline. The discoveries that require context, that build over decades of incremental measurement, that depend on understanding the physics before you can feel the wonder. Those discoveries arrive late, if they arrive at all. Ganymede's core is still forming. That sentence, if you understand what it means, is one of the most remarkable statements in modern planetary science. It describes a process that was not known to be occurring on any moon. It resolves a decades-long contradiction between formation models and dynamo models. It redefines Ganymede as an actively evolving world rather than a static relic. And it was published in May of 2026 in one of the world's leading scientific journals. How many people heard about it? How many people outside the planetary science community registered that the largest moon in the solar system was just revealed to be still assembling its own metallic core? How many documentaries mentioned it? How many headlines carried it? Compare that to any marginal detection of a possible plume on Europa. The asymmetry is stark, and it is not because the plume detection is more scientifically significant. It is because the plume detection is easier to visualize, easier to feel, easier to compress into the kind of emotional payload that travels fast. Ganymede does not travel fast. It accumulates. It builds. It layers one quiet revelation on top of another, year after year, study after study, until the aggregate picture is so large and so strange that anyone who finally looks at it closely cannot understand how they missed it for so long. That experience, the vertigo of realizing you have been looking past something enormous, is the emotional core of the darker reality. It is the feeling of discovering that the most extraordinary things are not always the ones that announce themselves. Sometimes they are the ones that were always there, always visible, always known by name, and simply never examined with the attention they deserved. In 2031, the JUICE spacecraft will arrive at Jupiter. It will spend 3 years studying the Jovian system. It will fly past Europa. It will fly past Callisto. And then, in 2034, it will do something no spacecraft has ever done. It will enter orbit around a moon other than our own. And the moon it will orbit is Ganymede. For 9 months, JUICE will circle this world at ever-decreasing altitudes. The first orbital phase will be a high elliptical orbit, sweeping over the poles and passing through the boundary where Ganymede's magnetic field meets Jupiter's plasma. The magnetometer will record the structure of the magnetopores, the shape of the auroral regions, the interplay between the intrinsic field and the induced ocean signal. Each orbit will bring new data. Each dataset will peel back another layer. As the weeks pass, mission controllers will lower the orbit. The spacecraft will draw closer to the surface. The radar will begin penetrating the ice, sending pulses downward and listening for the reflections that mark the boundary between frozen crust and liquid ocean. The gravity experiment will detect subtle variations in orbital velocity, millimeter per second changes caused by density differences deep inside the moon. From those measurements, scientists will reconstruct the thickness of each internal layer, building a three-dimensional model of Ganymede's interior that no previous mission could have produced. In the final phase, JUICE will enter a low circular orbit, just 500 kilometers above the surface. At that altitude, the magnetometer will be close enough to detect the faintest components of the magnetic field, the higher order multipoles that carry information about the geometry of the core, the subtle signatures of ocean circulation, the induced signals that reveal the conductivity and thickness of the buried saltwater layer. The camera will resolve features on the surface as small as a few meters across, revealing the texture of the grooved terrain, the morphology of the candidate cryovolcanic vents, the fine-scale geology that Galileo's cameras could only hint at. For 9 months, a spacecraft will orbit a world with its own magnetic field, its own magnetosphere, its own auroral glow, and an ocean larger than anything on Earth, circling 500 kilometers above a surface that may carry the chemical fingerprints of water that once rose from hundreds of kilometers below. It will be the closest, longest, and most detailed study of any outer solar system moon ever conducted. And when it is finished, JUICE will descend one final time, impacting the surface of Ganymede in late 2035, adding its own small mark to a world that has been collecting the scars of 4.5 billion years of cosmic history. If the mission succeeds, it will return the most detailed portrait of any outer solar system moon ever assembled. It will confirm or refine the ocean structure. It will characterize the dynamo. It will determine whether the ocean currents are detectable through their magnetic signatures. It will examine the candidate cryovolcanic sites to determine whether ocean material has reached the surface, and it will provide the first direct measurements capable of distinguishing between a core that finished forming long ago and one that is still growing today. The answers will matter. They will reshape our understanding of how moons work, how magnetic fields are sustained, how water behaves under extreme pressures, and how the internal evolution of a world can persist for far longer than anyone assumed possible. But the answers will also carry a quieter lesson. A lesson about what happens when attention is distributed unevenly, when the loudest signal captures all the resources and the quieter signal is left for later, when a world as large as a planet, as magnetically unique as anything in the solar system, as internally active as a body still forming its own core, is filed under later for 30 years because a smaller, more photogenic neighbor told a simpler story. Ganymede did not hide. It did not obscure its properties. It did not resist study. Every instrument that was pointed at it returned extraordinary data. The Galileo magnetometer found the dynamo in 1996. The Hubble telescope confirmed the ocean through auroral observations in 2015. The Juno spacecraft captured close-up imagery during its 2021 flyby. The 2025 and 2026 magnetic studies demonstrated that the ocean currents are potentially detectable. The 2026 core formation study proposed a mechanism that no other moon is known to share. The 2026 cryovolcanism study identified surface features that may connect the deep ocean to the outside. Each of these findings was published. Each was available to anyone willing to read it. None was hidden behind paywalls of secrecy or ambiguity. The information was always there. The world was always there, orbiting the same planet as Europa, visible in the same images. Known by the same name it has carried since Simon Marius proposed it in 1614. The darker reality is not inside Ganymede. It is in the space between Ganymede and the attention it was given. It is in the gap between what a world actually contains and how much of that content reaches the people who care about the solar system. It is in the quiet, persistent way that the most structurally extraordinary moon in our planetary neighborhood was treated as a footnote, while a smaller, less complex, but more visually dramatic neighbor became the face of an entire field of exploration. There is no villain in this story, no conspiracy, no deliberate act of suppression. Europa deserves its missions and its fame. The scientists who study Ganymede have been doing extraordinary work for decades, often with less funding and less public visibility than their colleagues working on Europa. The bias is not personal, it is structural. It is built into the way information moves through a system that rewards simplicity, speed, and visual impact over depth, patience, and layered understanding. And the correction is already underway. Juice is on its way. The 2026 studies have shifted the conversation. The scientific community is increasingly recognizing Ganymede not as Europa's companion, but as a world that demands its own narrative, its own framework, its own place in the hierarchy of solar system priorities. But the lesson remains, and it extends beyond moons, because the pattern that kept Ganymede in Europa's shadow is not unique to planetary science. It operates everywhere attention is scarce and complexity is high. The important things that are hard to explain will always lose ground to the less important things that are easy to feel. The discoveries that require context will always arrive later than the discoveries that fit in a headline. The worlds that hide their most extraordinary features beneath layers of ice and rock and magnetic silence will always be the last ones we truly see. Ganymede was never invisible. It was never unknown. It was never beyond the reach of our instruments or our understanding. It was simply quiet. And in a system organized around noise, quiet is easily mistaken for empty. It is not empty. It is a world larger than Mercury, a world with more water than Earth, a world with the only moon-generated magnetic field ever detected, a world whose core is still forming, a world whose ocean currents may be writing their signatures in magnetism, a world whose surface may bear the traces of eruptions from a deep interior that has been evolving since before life existed on this planet. It has been there the entire time, orbiting Jupiter, reflecting sunlight, generating a magnetic field that no other moon possesses, carrying inside itself a layered, pressurized, magnetically active interior of staggering complexity. And the most unsettling truth is not that Ganymede is bigger than Europa. It is not that it has a stronger scientific case for structural complexity. It is not that it has been underappreciated or underexplored. The most unsettling truth is simpler than any of that. One of the largest, strangest, and most consequential worlds in the solar system was never hiding. It was standing in plain sight. And for decades, when people looked at Jupiter and asked which moon mattered most, they looked right past it. Not because Ganymede was concealing anything, but because the answer it offered required more patience than the question seemed to demand. The patience is arriving now. The spacecraft is on its way. The studies are being published. The instruments are being calibrated. And Ganymede, the quiet one, the overlooked one, the moon that most people know by name but have never truly considered, is about to become the most closely studied world in the outer solar system. When it does, when the data comes back, when the magnetic maps are drawn and the ocean currents are traced, and the core structure is resolved, the picture that emerges will not be of a moon that was hiding a darker reality. It will be of a world that was offering one, openly, continuously, for as long as anyone cared to look. The question was never what Ganymede was hiding. The question was why it took so long to look.